Imagine a world where the very rules governing reality are not as solid as we believe. A world where the most elusive particles, the ghostly neutrinos that constantly bombard our planet, are behaving in ways that defy everything we thought we knew. What if I told you that a groundbreaking discovery has not only confirmed the existence of a bizarre neutrino anomaly, but also holds the potential to rewrite the textbooks of physics, unlock the secrets of dark matter and dark energy, and even redefine our understanding of the universe's birth? Buckle up, science enthusiasts, because the story we're about to unravel is nothing short of revolutionary. You know, it's quite humbling to think that some of the most profound scientific breakthroughs have stemmed from what initially appeared to be failures or inconsistencies. Remember the prediction of the neutrino itself. It wasn't some grand theoretical pronouncement out of the blue. No, it arose from a seemingly problematic energy deficit in particle decays. Scientists, scratching their heads, realized that the energy budget simply wasn't adding up. The brilliant, almost audacious, leap was to propose the existence of an invisible particle carrying away that missing energy. As the quote in our story aptly puts it, "Look, folks, I can't explain this, let's make some up." And you know what? Sometimes that's precisely what genius looks like, daring to imagine the unseen to explain the inexplicable. Fast forward to today, and we find ourselves on the cusp of another paradigm shift, driven by the equally unexpected behavior of these very same neutrinos. The Majorana 1 quantum chip, a marvel of modern engineering, has detected neutrinos exhibiting behavior that throws a massive wrench into the well-oiled machinery of the standard model of physics. These subatomic particles, those ethereal messengers from the cosmos, were observed switching between their different flavors, electron, muon, and tau, at frequencies that are utterly impossible according to our current understanding. It's like discovering that a fundamental law of nature has a loophole, a secret back door we never knew existed. Now, this monumental discovery wasn't just a stroke of luck. It was the result of an ingenious synergy between cutting-edge quantum technology and a scaled-down version of a truly mind-bending concept, the Dyson Sphere. The Dyson Sphere, initially theorized by the brilliant physicist Freeman Dyson, envisioned gigantic structures built around stars to capture their immense energy output. While constructing a full Dyson Sphere remains firmly in the realm of science fiction for now, the researchers developed a scaled prototype, a sophisticated system designed to concentrate stellar energy at levels never before achieved. Think of it like a cosmic magnifying glass, focusing the sun's power onto a tiny point. When this unprecedentedly concentrated stellar energy was channeled into the Majorana 1's quantum detection grid, it unlocked a level of sensitivity 300 times greater than any neutrino detector that came before it. Imagine trying to see a faint whisper in a crowded room versus being in a silent chamber with highly sensitive microphones. The difference in clarity is staggering. The quantum chip, bathed in this focused stellar radiation, gained the unprecedented ability to process the delicate quantum states of neutrinos, something that was simply impossible with previous technology. It's like finally having the right kind of eyes to see a hidden world that has been all around us. What truly elevates this finding from an intriguing anomaly to a potentially revolutionary discovery is its robust verification. 7 independent research facilities, scattered across the globe, have now confirmed these astonishing results using entirely different methodologies. This isn't just one lab with a quirky reading. It's a chorus of scientific voices echoing the same unexpected tune. This consistent observation across diverse experimental setups effectively eliminates the nagging doubts of experimental error or equipment malfunction. It's like having multiple witnesses corroborate the same unbelievable event. The more independent confirmations, the stronger the evidence becomes. So why does this all matter? Why should we be so excited about the seemingly strange behavior of these tiny, elusive particles? The implications are profound. If these neutrino behaviors are indeed real, then our fundamental understanding of particle physics, the very bedrock upon which our knowledge of the universe is built, is incomplete. It's like realizing that a crucial piece of a massive puzzle has been missing, and now we've finally found it, but it doesn't quite fit the picture we had in mind. This discovery could hold the key to unlocking some of the most enduring mysteries in science, from the enigmatic composition of dark matter, the invisible substance that makes up a significant portion of the universe, to the baffling asymmetry of matter and antimatter, the reason why our universe is filled with stuff instead of annihilating itself into pure energy. We could be on the verge of rewriting physics textbooks worldwide, ushering in a new era of understanding. And speaking of rewriting textbooks, the implications extend far beyond the realm of particle physics. As Dr. Michio Kaku, a name synonymous with cutting-edge science, aptly put it, this isn't just another particle discovery. It's shaking the very foundation of quantum physics. The ripples of this discovery are spreading outwards, touching cosmology, the study of the universe's origins and evolution, astrophysics, the study of celestial objects and phenomena, and even our most basic understanding of how the universe came to be. Leading physicists believe that this neutrino anomaly could provide explanations for several long-standing puzzles, including the bizarre interconnectedness observed in quantum entanglement experiments, where particles seem to be linked across vast distances in ways that defy classical physics, and the subtle inconsistencies in the cosmic microwave background radiation, the faint afterglow of the Big Bang that holds crucial clues about the early universe. Think about quantum entanglement for a moment. It's often described as spooky action at a distance, where two entangled particles, no matter how far apart, seem to instantaneously influence each other. This has baffled scientists for decades, seemingly violating the speed of light, the ultimate speed limit in our universe. Could this strange neutrino behavior be somehow intertwined with this quantum enigma, offering a new perspective on the fundamental nature of reality and the interconnectedness of everything? Similarly, the cosmic microwave background radiation, while providing strong evidence for the Big Bang theory, has some subtle variations that don't perfectly align with our current models. Could the anomalous behavior of neutrinos, particles that were abundant in the early universe, hold the key to resolving these discrepancies, providing a more complete picture of our cosmic origins? The significance of this discovery truly crystallized during an emergency symposium held at the prestigious Institute for Advanced Study, a place where some of the greatest minds in history have gathered. The mood was one of both exhilaration and profound caution. As one of the speakers emphasized, while the excitement is palpable, we must approach these findings with extreme rigor. If verified through further independent methods, this neutrino anomaly isn't just an incremental addition to our knowledge of physics. It fundamentally challenges our most basic assumptions about how the universe operates at its most fundamental level. It's as if we've been reading the cosmic blueprint upside down all along, and this discovery is finally allowing us to see it from the correct perspective. The potential implications are mind-boggling. Could this mean that our understanding of fundamental concepts like time and gravity needs a radical overhaul? Could time, as we perceive it flowing in one direction, have a more complex nature? Could gravity, the force that governs the large-scale structure of the universe, be merely a secondary manifestation of a deeper, more fundamental force that we have yet to detect? These are the kinds of profound questions that this neutrino anomaly is forcing us to confront. This finding doesn't just impact the abstract world of theoretical physics. If the neutrino anomaly holds true, it could have far-reaching consequences for our understanding of stellar formation, the processes that give birth to stars and galaxies. It might even shed new light on the mysterious dark energy, the force believed to be responsible for the accelerating expansion of the universe, and offer new insights into the information paradox of black holes, those enigmatic regions of spacetime where gravity is so intense that nothing, not even light, can escape. Unsurprisingly, the theoretical physics community is buzzing with activity, with prominent physicists already proposing potential explanations and calling for further investigations. Dr. Lisa Randolph from Harvard, a leading expert in theoretical particle physics and cosmology, suggests that the anomaly might be explained by higher dimensional interactions, a concept that arises in string theory, a theoretical framework that attempts to unify all the fundamental forces and particles by postulating the existence of extraspatial dimensions beyond the three we experience. Meanwhile, Dr. Brian Greene, another renowned theoretical physicist and popular science communicator, has called for an immediate recalibration of all major neutrino detectors worldwide to attempt independent verification using different methodologies. The theoretical physics community hasn't been this energized since the confirmation of the Higgs boson in 2012, a discovery that filled a crucial gap in the Standard Model. So, what does this mean for the Standard Model of particle physics, that incredibly successful yet incomplete framework that has governed our understanding of the subatomic world for decades? This neutrino anomaly represents the most significant challenge to the Standard Model in recent memory. For years, the Standard Model has successfully predicted virtually every particle interaction we've observed, a testament to its power and accuracy. This unexpected neutrino behavior suggests one of two possibilities. Either there exists an entirely new fundamental force beyond the four we currently know: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, or neutrinos are interacting with hitherto unknown particles that reside outside the current framework of the Standard Model. It's like discovering a new character in a play that doesn't fit any of the existing roles, forcing us to rewrite the script. Furthermore, this discovery could completely transform dark matter research. The anomalous neutrino oscillations, that strange switching between neutrino flavors, actually match some theoretical predictions for how neutrinos might interact with dark matter particles. This provides the very first experimental pathway to potentially detecting dark matter directly, rather than just inferring its existence through its gravitational effects on visible matter. For years, dark matter has been the invisible elephant in the room, making up the vast majority of the matter in the universe, but remaining stubbornly elusive. This neutrino anomaly could finally give us a way to see it. Researchers at CERN, the European Organization for Nuclear Research, home to the Large Hadron Collider, are already modifying their detection protocols based on these exciting findings, eager to explore this potential link between neutrinos and dark matter. Our understanding of the early universe, the tumultuous period immediately following the Big Bang, also faces potential revision in light of this neutrino anomaly. Neutrinos played a crucial role in the formation of matter in those first fleeting moments. If their fundamental properties differ from what our current models predict, then our cosmological simulations of universal expansion, galaxy formation, and the distribution of matter throughout space may need complete recalculation. It's like realizing that a key ingredient in the recipe for the universe wasn't quite what we thought it was, potentially altering the entire cosmic dish. The subtle patterns in the cosmic microwave background radiation, those echoes of the Big Bang, might finally be fully explained by incorporating this new understanding of neutrino behavior. Beyond the theoretical implications, this discovery could also lead to revolutionary technological applications. If this anomaly confirms the existence of new particle interactions or properties of neutrinos, it could pave the way for breakthroughs in energy production, perhaps through harnessing these novel interactions. It could also enhance the stability and capabilities of quantum computing, which relies on the delicate and often fleeting quantum states of particles. And perhaps more speculatively, it might even open up possibilities for theoretical faster-than-light communication, if the anomalous neutrino behavior is linked to entanglement in unexpected ways. Several tech companies, always on the lookout for the next disruptive technology, have already filed provisional patents for technologies based on these newfound neutrino properties, despite the preliminary nature of the findings. But here's the truly mind-blowing part. The aspect of this discovery that even seasoned scientists like Dr. Kaku admitted they didn't see coming: the implications for quantum gravity. The anomalous neutrino behavior exhibits properties that perfectly align with the requirements for various quantum gravity theories, those ambitious frameworks that attempt to reconcile the seemingly incompatible realms of quantum mechanics, the physics of the very small and general relativity, Einstein's theory of gravity that governs the very large. For decades, testing these quantum gravity theories has seemed virtually impossible due to the incredibly high energies involved. This neutrino anomaly, unexpectedly, might provide a backdoor into this elusive domain, offering experimental evidence for theories that were previously purely mathematical constructs. The Majorana 1 quantum chip itself represents a quantum computing breakthrough that goes far beyond conventional designs. Unlike traditional quantum processors that rely on superconducting circuits, which are often susceptible to noise and decoherence, the Majorana 1 utilizes topological qubits based on Majorana fermions, exotic particles that are their own antiparticles. This unique topological architecture grants the chip an extraordinary resilience, allowing it to maintain quantum coherence, the fragile superposition of quantum states crucial for computation, for unprecedented periods while simultaneously processing complex quantum states across multiple dimensions. Think of it as a quantum computer that is not only incredibly powerful but also remarkably stable. What truly sets this discovery apart is the ingenious integration of this advanced quantum chip with the experimental Dyson Sphere program framework. This scaled prototype of the Dyson Sphere concept doesn't aim to envelop an entire star. Instead, it employs specialized arrays to capture and intensely focus stellar energy onto a specific area. Previous attempts to detect this neutrino anomaly failed for a fundamental reason: insufficient energy density within the detection fields. Conventional neutrino detectors typically rely on massive tanks of purified water or liquid argon, patiently waiting for the rare instance when a neutrino interacts with an atom within the tank. The Majorana 1, with its DSP integration, creates an actively energized detection field that effectively illuminates neutrino interactions that would otherwise remain invisible to conventional detectors. The innovative detection method works by establishing a delicate quantum entanglement between the detection field, energized by the focused stellar radiation, and incoming neutrinos. As neutrinos pass through this field, their quantum states briefly entangle with the detector's topological qubits. This fleeting entanglement leaves subtle information signatures within the quantum state of the detector, signatures that the Majorana 1 processor can then decode with unprecedented precision. It's akin to upgrading from a still camera trying to capture a fleeting moment to a high-speed video camera that can record every subtle nuance of a fast-moving object. The international team behind this groundbreaking discovery is a testament to the power of collaborative science, bringing together expertise from diverse fields like quantum computing, astrophysics, and particle physics. The team is led by Dr. Elena Rodriguez, a pioneering figure in quantum computing who previously worked at CERN. The collaboration includes researchers from prestigious institutions like MIT, Caltech, the Chinese Academy of Sciences, and CERN. Notably, several members of the team were previously involved in earlier, ultimately unsuccessful, attempts to reconcile quantum mechanics with general relativity, experience that proved absolutely crucial in recognizing the profound significance of the anomalous neutrino data. They had the background and the intuition to see that something truly extraordinary was happening. Verification efforts are already in high gear at major research centers around the world. The IceCube Neutrino Observatory, buried deep within the Antarctic ice, is reconfiguring its vast array of detectors to search for similar anomalies in the flood of neutrinos passing through our planet. Meanwhile, the Hyperkamiokon detector in Japan and the Deep Underground Neutrino Experiment (DUNE) facility in South Dakota are racing to implement modified detection protocols specifically designed to verify the Majorana 1 findings. The peer review process, the rigorous scrutiny by other experts in the field that is the cornerstone of scientific validation, has been accelerated, with preliminary research papers already submitted to prestigious journals like Nature, Physical Review Letters, and Science. Initial feedback from the scientific community is expected within the next couple of months, with the potential for an official announcement of verified results anticipated within 4 months. To further address these extraordinary findings, an emergency session of the International Conference on High Energy Physics, the premier global gathering for particle physicists, has been scheduled. The broader scientific investigation will proceed along 3 parallel tracks. First, theoretical physicists are intensely working to develop new mathematical models that could potentially explain the anomaly within the existing frameworks of physics or through minimal, yet significant extensions. Second, experimental teams are designing novel tests specifically aimed at probing the boundaries of this unexpected neutrino behavior, seeking to understand its limits and characteristics. Third, cosmologists are re-examining existing observational data from telescopes and satellites, looking for previously overlooked evidence that might correlate with these neutrino findings, potentially revealing hidden connections in the cosmos. The Majorana 1 team itself is not resting on its laurels. Having already upgraded their detection configuration based on their initial results, they have planned 5 critical follow-up experiments. These experiments aim to test neutrino behavior under a range of varying energy conditions, meticulously measure interaction rates across different atomic elements, examine potential correlations between the anomaly and the intensity of cosmic rays bombarding Earth, investigate the possibility of seasonal variations in the observed anomaly, which could hint at an extraterrestrial source or influence, and even attempt to deliberately induce similar anomalous behavior through controlled quantum field manipulation within their experimental setup. Looking ahead, predictions within the scientific community suggest 3 possible overarching outcomes. The most thrilling possibility is that this anomaly represents a truly fundamental new discovery that will reshape our understanding of physics at its deepest levels, opening up entirely new avenues of research and technological innovation. Another possibility is that the observed behavior, while unexpected, can ultimately be explained through more complex and nuanced applications of existing theories, pushing the boundaries of our current models, but not necessarily requiring a complete overhaul. The third, and perhaps most intriguing, possibility is that this anomaly reveals an entirely new aspect of reality, a hidden layer of the universe that connects previously disconnected domains of physics in ways we are only beginning to glimpse. Regardless of which of these possibilities ultimately proves to be correct, this moment undeniably represents one of the most exciting frontiers in modern science. It's a genuine opportunity to profoundly expand humanity's understanding of the fundamental nature of our universe, to peel back another layer of the cosmic onion. Neutrinos, once considered ghostly and almost undetectable, are now taking center stage, potentially holding the key to unlocking some of the universe's most closely guarded secrets. Just as the development of quantum mechanics revolutionized our understanding of the atom and led to transformative technologies in the 20th century, these findings could launch us into an entirely new era of discovery, with implications we can only begin to imagine. We stand at the threshold of reimagining the very fabric of reality. To truly appreciate the significance of this discovery, it's helpful to have a bit of background on neutrinos themselves. These are subatomic particles belonging to the lepton family, akin to electrons but lacking any electric charge. They are among the most abundant particles in the universe, with trillions constantly streaming through every square centimeter of Earth each second, a silent, invisible rain from the cosmos. Their defining characteristic is their incredibly weak interaction with normal matter, which is what makes them so difficult to detect. They can pass through planets almost unimpeded, earning them the nickname ghost particles. Neutrinos come in three distinct flavors: electron neutrinos, muon neutrinos, and tau neutrinos, each associated with a corresponding charged lepton. The history of neutrino research is a fascinating tale of theoretical prediction and painstaking experimental verification. In 1930, the brilliant physicist Wolfgang Pauli first proposed the existence of the neutrino to explain an apparent violation of the law of energy conservation in radioactive beta decay. It was a bold hypothesis, suggesting an unseen particle was carrying away the missing energy. However, it wasn't until 1956, a quarter of a century later, that the existence of neutrinos was experimentally confirmed by Clyde Cowan and Frederick Rains in a landmark experiment. In the 1960s, Ray Davis's pioneering solar neutrino experiments revealed a perplexing mystery. Only about 1/3 of the expected number of neutrinos from the Sun were being detected on Earth. This solar neutrino problem puzzled scientists for decades, until it was finally resolved in 2001 with the groundbreaking discovery of neutrino oscillation, the ability of neutrinos to spontaneously change between their three flavors as they travel. This discovery not only solved the solar neutrino problem, but also proved that neutrinos have a tiny but non-zero mass, a finding that contradicted the original predictions of the Standard Model. The Standard Model of particle physics, developed throughout the 1970s, is a remarkably successful theoretical framework that classifies all known elementary particles, the fundamental building blocks of matter, and describes three of the four fundamental forces of nature: electromagnetism, the weak nuclear force responsible for radioactive decay, and the strong nuclear force, which binds quarks together to form protons and neutrons. It elegantly organizes matter particles into two main groups: quarks, which make up protons and neutrons, and leptons, which include electrons and neutrinos. The forces are mediated by force-carrying particles called bosons. Despite its immense success in predicting the existence of particles like the Higgs boson, which was finally discovered in 2012 and confirmed the mechanism by which particles acquire mass, the Standard Model is not a complete theory. It cannot explain the force of gravity, the existence of dark matter or dark energy, and it originally struggled with the non-zero mass of neutrinos. The Dyson Sphere concept, as mentioned earlier, was first proposed by the visionary physicist Freeman Dyson in a seminal 1960 paper. He envisioned it as a hypothetical megastructure, perhaps a solid shell or a dense swarm of orbiting collectors, that would completely encompass a star, allowing a civilization to capture and utilize most or all of its prodigious energy output. While constructing a full Dyson sphere remains far beyond our current engineering capabilities and might even present insurmountable technological challenges, the Dyson Sphere program, in the context of this neutrino discovery, represents a scaled-down, experimental application of these principles. Rather than surrounding an entire star, the program utilizes specialized arrays of mirrors and lenses to capture and focus stellar energy onto a much smaller target area, creating energy densities at levels previously unachievable on Earth. This concentrated energy then becomes a crucial tool for advanced particle detection, illuminating the subtle interactions of elusive particles like neutrinos. Traditional neutrino detection methods have long faced significant limitations. Detectors like Super Kamiokande in Japan and Borexino in Italy rely on massive tanks of ultra-pure water or liquid scintillator to increase the probability of a rare neutrino interaction with an atomic nucleus within the detector. These detectors require enormous volumes of carefully shielded material to minimize background noise from cosmic rays and other sources of radiation. Moreover, they can only observe neutrinos passively, waiting for chance encounters. They primarily detect neutrinos through charge current interactions, where a neutrino converts a neutron into a proton, emitting a charged lepton, an electron, muon, or tau, thus missing many other types of neutrino interactions. The energy thresholds of these conventional detectors also limit their ability to detect lower energy neutrinos, and often, the directional information of the incoming neutrino is difficult to precisely determine. The Majorana 1 quantum chip, with its innovative integration with the DSP Dyson Sphere program framework, overcomes many of these fundamental limitations. Its active quantum field detection, powered by the concentrated stellar energy, vastly improves the signal-to-noise ratio, allowing the detection of much fainter neutrino interactions amidst the background. Crucially, it goes beyond simply detecting the products of neutrino interactions. It can directly probe the quantum states of the neutrinos themselves through the quantum entanglement established with the detection field. This allows for a much more comprehensive and detailed observation of neutrino behavior, including the subtle oscillations between flavors and other quantum properties that were previously inaccessible. It's a paradigm shift from passively waiting for a neutrino to bump into something to actively illuminating and observing its fundamental characteristics. The detection of this anomalous neutrino behavior by the Majorana 1 quantum chip is undeniably a pivotal moment in modern physics. By ingeniously leveraging cutting-edge quantum computing technology with the experimental Dyson Sphere, programs unprecedentedly concentrated energy collection, scientists have observed patterns in neutrino behavior that directly challenge our fundamental understanding of particle physics as codified in the Standard Model. This groundbreaking discovery has the potential to unlock profound insights into some of the universe's deepest mysteries, including the nature of dark matter, the long-sought theory of quantum gravity, and the intricate processes that governed the early formation of our universe. This moment may very well mark the beginning of the next great revolution in physics. Just as the development of quantum mechanics at the start of the 20th century transformed our understanding of the atomic and subatomic realms and led to a cascade of technological advancements, these surprising findings could launch us into an entirely new era of scientific discovery, with implications that extend far beyond the laboratory. We stand at the threshold of fundamentally reimagining the nature of reality itself. Whether this intriguing anomaly ultimately leads to a significant extension of the standard model, provides crucial experimental validation for existing theoretical frameworks like string theory, or most excitingly, opens up entirely new theoretical frameworks that connect previously disparate domains of physics, its importance cannot be overstated. From the unexpected detection through the creation of quantum entanglement fields bathed in focused stellar energy, to the ongoing worldwide verification, efforts now underway at leading research institutions, we are witnessing science at its most thrilling and dynamic. When careful observations challenge our most established theories and push the boundaries of human knowledge towards a deeper and more complete understanding of the cosmos. For those of you who are as captivated by this unfolding scientific saga as we are, major announcements and updates are expected in the coming months as the independent verification experiments reach their conclusions and the rigorous peer review processes are completed. The next meeting of the International Conference on High-Energy Physics is almost certain to feature these findings prominently, potentially marking a historic moment in our collective quest to unravel the universe's deepest secrets. If this story of the ghostly neutrino and the revolutionary technology that unveiled its secrets has fascinated you, then you definitely won't want to miss our upcoming video that delves deeper into how Dyson Sphere program technology, beyond its role in this discovery, is poised to revolutionize various fields within particle physics and beyond. Make sure to hit that subscribe button right now and turn on the notification bell, so you'll be among the first to know when we release more groundbreaking scientific revelations just like this one. What do you think this neutrino anomaly truly signifies? Could this be the key to finally unifying quantum mechanics and general relativity? What other seemingly impossible discoveries might be lurking just beyond the horizon, waiting for the right technology to bring them to light? Share your thoughts and theories in the comments below. We love hearing your perspectives. And as we continue to explore the wonders of the universe together, I wish you all good health, clear thinking, and an unwavering curiosity about the amazing world around us. Stay tuned for more incredible scientific adventures.